Is it recording now? Okay.
Yeah. Actually, hold up.
Hold on.
That's really funny.
Spring 2020. Oops.
Exposed. I just need to make sure that's not connected to my
Hello everyone. I think we can get started. Welcome to CS170 review, midterm review. Today we're focusing on graph, and we broke down the topics into four. We broke down the section into four topics: the DFS, BFS, DAG topological sort, strongly connected components, and also shortest path. As you may know, for this midterm, minimum spending tree and greedy algorithm will not be covered. So in this section in particular, the focus should be on the shortest path algorithms. And if you have any questions during the review section, you can raise your hand, and we'll have TAs who come to you and answer your question. Also, we have a live Piazza thread where you can post your question, and the review slides are also posted already. And you can check to make sure you have access to that. And for each topic, we'll go over the concept briefly, and then there are a couple of review problems that vary in difficulty. Okay, I think we will start with DFS and BFS, which stands for depth first search and breadth first search. And this algorithm on the left, the explore algorithm, will give you the pre-order and post-order. So for this is the explore algorithm for DFS using the recursive stack. So for each node that you have not visited, when you first check the node, you increment the clock by 1, and then you label it with its pre-order, and then after you finish exploring it, you increment the clock again, and then add the post-order. And so this is the algorithm to calculate pre-order and post-order. And on the right is the algorithm for breadth first search, BFS. The depth first search uses a stack, and the BFS uses as priority queue. Right. And so DFS, it's so the node starts the path that this algorithm gives you does not guarantee that this is the shortest path, which is not true for BFS. BFS will always give you the shortest path, assuming the weight for each edge is only 1. But for DFS, that's not a guarantee. And in a DAG, every edge leads to a vertex with a lower post-order number. So that's why the descending post-order is the topological order of any DAG. We'll cover DAG more carefully later. And any questions so far? Okay. And you also need to know the different types of edges in the DFS tree. So all the edges in the tree are called the tree edges, and the back edges is a node that leads to an ancestor in the DFS tree. So the back edges are what create a cycle in this graph. And forward edge is when an ancestor point to a child, not an immediate child, but forward edges lead from a node to a non-child descendant, yeah. And cross edges are everything else, basically. Any questions? Yes?
I looked at an old exam, and they didn't draw in anything else but the tree edges.
Yes, yes.
If the exam says draw out the DFS tree, then just the tree edges,
right? Right, yeah, that's only the tree edges, yes. A tree will only have the tree edges, yes. And you can determine the type of edges by looking at the pre-order and post-order. So if the pre-order, post-order is of the tree edge and the back edge are the exact opposite. And that's why it creates a cycle because, yeah. And the cross edge is well, when you explore one node and then you finish it and you move on to the next one. So that's a cross edge. And a directed graph is a DAG if and only if it does not have a cycle. Yeah. And so the concept, the definition of DFS should be relatively clear. And now we can move on to some practice problems. So I'll give 2 minutes to look at this problem. Here's a hint. There's a question. Just a question. Okay. So does anyone want to answer this question? Yeah. Yes, exactly. So we use the DFS algorithm. So we run the DFS search on the graph, and we do pre-order and post-order with the Explorer algorithm that you just saw before. And then you can, because as the hint points out, if it's a tree, if it's an tree edge or forward edge, the pre-order and post-order are in a specific pattern. Any questions? Yes.
Yeah, if it is a tree, then should it have post whatever edge that back edge or whatever it's called?
No, if it's a tree, it only has tree edges. But when you create the tree while running well, yeah, doing the algorithm, you will see edges that are not inside the tree, and those edges might be back edges or forward edges or cross edges. But those edges are not included in the tree. Yeah. This can be directed or not directed. Yeah. Yes. No, it would never be the same. Yeah. So the less than or equal to sign should just be the less than sign. It will, two nodes will never have the same pre-order or post-order. Moving on to the next question. I'll give 2 minutes to work on this problem. So we'll come back to this problem. Anyone has any idea on number 1? Is it true or false? Yes, it's false. So in these questions, you should try to think about the extreme cases. For example, when a graph is a complete graph where between every node there's an edge, then regardless of how you break ties, your DFS tree will just be a path, like a straight line, right? So if you have a tree that's not in this shape, then there's no way that you can create this. Create this tree with this graph, with a complete graph. Does it make sense? Any questions?
What do you mean by break ties?
So break ties is when you start exploring a node, there might be different options you can take. So there might be different edges connected to that node. So which edge do you go through first is how you break ties. So in past problems, we mainly break ties by alphabetical order. So for example, if the node is A and is connected to a vertex B and a vertex C, so we'll explore B first because AB comes before AC. Yeah. Yes.
I don't understand what the first sentence is. What is it? How do you construct that tree? All the vertices?
You have an arbitrary tree. You can create a tree with these vertices, and we're saying so for any tree. So as long as it's a tree, and you have this graph that have to share the same vertices as this tree, and there's a way to break ties in the DFS that will up to T. So for okay. So suppose my graph has 4 nodes, and I can create a tree like this. This is a valid tree, but with my if my original graph with these 4 nodes is a complete graph, then when you run DFS algorithm on it, it will always give you a path. So this will always look different from this tree. That's why number 1 is false. Yes. Yes, I'm saying if this graph G is a complete graph where every node is connected by an edge. Okay, so moving on to number 2. Do you think it's true or false? Yes, it's false again. So with the same example, this tree, if we're running BFS on a complete graph, the tree will look like a root node and then connected to different nodes. Right? So if your tree doesn't look like this, for example, if the tree given is a path, is a line, then this doesn't work. So that's so number 2 is false. Any questions on this problem? Yes.
So basically, this question is kind of referring to the fact that you don't have DFS.
Yes. Yes. Exactly. Yeah. Any last minute questions on BFS or DFS? Okay, so we'll move on to DAG, the directed acyclic graphs.
Can you hear me? Okay. Oh my. Any questions before I start on this? Okay, so I'm just gonna go over it pretty quickly because I feel like it's pretty easy stuff. So can we quiet down a little bit, please? Okay, so directed acyclic graph basically means that a directed graph that doesn't have any cycles. And why do we study these kind of graphs? Because these kind of graphs, well, first of all, it represents some kind of questions pretty nicely. We'll see later with an example. And also, we can see that, I don't know. So yeah, it's pretty far away. So a good thing about these kind of graphs is that it can be topologically sorted, which means that we can arrange these nodes on some surface and so that all the edges points to one direction. So like, this is a very typical example of a directed acyclic graph. This is basically the course you're able to take in this department. And well, you don't want there to be a cycle if, for this case, because then you basically cannot take any class in that cluster then, right? So yeah, so the arrow here means that, well, it requires this course to take this one. So with topologically sorting, you can basically figure out an arrangement so that you can take class in a certain order so that all the requirements are fulfilled before you take the next class. Okay, so this is what I'm talking about. And the way to find the topological sorting is just DFS reverse post order. Do anyone see why? Anyone? Yeah? All right. So basically, remember that so DFS post order basically means the post number, right? So like the highest post number always in the source. So if it reverse it, or like basically figure out each of the source first, and then like arrange it on that. It's not important here, but we'll see later. So strongly connected components basically means that so like, well, for undirected graph, this is like a trivial sense. As long as it's connected, it's strongly connected. But for directed graphs, this means that for every vertex in this component, it can go to any other component, and like for every vertex. So yeah, basically, this is not a strongly connected component because you cannot go from here to here. But now this is a strongly connected component. And a nice property that we're studying here is that every directed graph can turn into a directed acyclic graph of its strongly connected components. It's a mouthful, but basically means that if this is a strongly connected component, we can just represent it with a single vertex, and we can turn the graph over here into something like this, so that it is a directed acyclic graph, and it can efficiently be processed or whatever. Okay. So see, this is an example from textbook. Any questions? Conceptual questions on this? No? Good. Okay, so I claim the existence of such decomposition of graphs, but how do you find it? So these things are also on a textbook. So basically, first step is run depth first search on the reverse graph of G to get the post number orders. And remember that the highest post number lies in this source component. And then, since it's since we find one node in the source component in the reverse graph, it means that we find the one vertex in the sink component in the original graph. And then with one of those vertex, then you can just find whichever vertex it can reach to, so that all those vertices will be in the same sink component in the original graph. And then you can just remove that and repeat this process. And that gives you the strongly connected components of this entire graph. Questions? Yes? We're talking about undirected graphs, or? For undirected graph, it's actually trivial. I don't know, but like, because as long as it's connected, if there's any paths in it, then everything is connected because you can go any directions. So like you can just check if the graph is connected. If it is, then it's just the one big strongly connected components. Okay.
Do you mean that we need to run DFS twice to get a SCC?
Uh,
First time is to get a post-order numbers, and the second time is to get a CC number.
Potentially you have to run it many times, but none of like only one of them goes through all the vertices. So suppose you have a huge graph that is something like this. So this is, I already represented in the directed acyclic graph version. So there's many components in here. Right. Do you guys understand this? This is very abstract. Okay, so basically, first run of DFS, I find one of those vertices in this sync component. And then from here, I run a DFS from here and figure out what what else is in the same sync component. So this is a DFS run that figures out this part of the graph. And then from the rest of the post-order numbers, we can figure out what's like maybe one vertex in here. And then from here we can find all the vertex that it can reach to and find a component here, and then repeatedly for the entire graph. So it runs maybe many DFS runs, but like the first one, only the first one goes through all the vertices and edges. The rest just explores like one portion of the graph. So in total, it only goes through each of the vertex twice. So it's the same runtime as DFS. Okay. Yeah, questions? That one.
Do SCCs always consist of cycles?
Yes, for directed graphs, yes. Because if there's no cycle, it's just a single pass. You cannot get from the end to the back. Okay, so that's enough question for now. If you have more questions, feel free to post on Piazzas. Those guys can answer it. Well, let's just spend a couple minutes just do this mechanical DFS questions. You have to familiar yourself with this because you see a lot of those similar questions on exams and homework and stuff. If you don't want to do that, just relax. Okay. Do we need more time? Do anyone need more time? Okay, so I'll just reveal the answer and you can check yours with it. I can go through it a little bit. So I think everything is breaking tie alphabetically, right? So starting from A, you can go to B or D, and then, well, first you mark the pre-number of A to 1, and then you go to B, mark the pre-number of B to 2, and then B can go to E, and then mark E to 3, and E can go to where? H. H is 4. And from H, you cannot go anywhere that hasn't been visited, so you just starting to go back. So you assign the post number of H to be 5, and go back to E. E doesn't go anywhere, so post number is 6. And E goes back to B, and B got popped off too, so the post number of B is 7 again. Oh, okay, spoiler. So the post number B got assigned to 7, and it goes back to A and explores some other routes. I'll just leave it here for a second, and you can check your answer. Next question.
Difference between the types of paths, like a tree, forward, backward.
Okay, I'll explain that later. Is there a question over there? Wait, what?
So, like on exams, are all the X's labeled
I think on the exam will specify which order you're going to break time. If not, I guess it's the help. Oh yeah, so I'll explain that part later too. Okay, cool. So okay, so pay a little attention over here. I'm gonna say something very important. It may change your life or not. I don't know. Okay, do we all remember this graph? Yes? Okay, so a lot of people ask me what are the different types of edges and basically what they mean. I'm gonna explain it here once again because it can be very confusing. So the most important thing is that all the edge types are related to the DFS traverse tree. So if your tree is so for this graph, there's two ways to traverse it. Actually, many ways to traverse the tree, but let's look at two of the ways to traverse it. So if our DFS traversal goes here first, and then here, right? So now it explores all the nodes, right? And so the tree edge here, as in the tree edge in the DFS tree, are these three edges, okay? So everything else that is not in bullet form is not in the tree, right? So is that clear? So for these edges, we can assign them different types, right? So if you can look at this, so this C vertex here is actually an ancestor of A, and there's an edge from C to A that points back. So this is what we call back edge. Yeah, question?
Does the concept of back versus forward edge matter if it's a contracted graph, or
Yeah, it doesn't
are they
matter.
essentially the same thing?
Yeah, it doesn't. Yeah. Okay. So this is it. This is the back edge. Sometimes you see just dotted lines in a graph. It means that this edge is in the graph, but not in the DFS traverse tree. Is that clear? Yes? And also, similarly for these other edges, these are not in the tree, and this goes from A to D, which is from an ancestor to a descendant. So this is the forward edge. And this goes from, well, they don't have hierarchical relations, so it's just cross edge. Is that clear? This is very important. Those edge types are with respect to one specific DFS tree. So if I change my DFS tree a little bit, I say I don't break tie alphabetically. So I traverse like this. So I go to B first, and then go to D, and then go to C. So this is my DFS tree. What would these edge be now? So this is no longer a tree edge anymore. This is a forward edge. And this is no longer a cross edge. This is in a tree, so it's a tree edge. Is that clear? Okay. So, yeah. Question?
Yeah, so let's say you started at J instead, right?
Mm-hmm.
S from J to A would then be a tree edge.
Yeah, if you start from J, then JA will be a tree edge. Yeah. Okay. Okay, if there's no more questions, I'll go on now. So you've seen this graph many times before we even see the question. So this is the strongly connected directed acyclic graph of the strongly connected components. So if you can see that J here is one connected component, and this little circle here is one connected component. Everything here can reach to everything here. So this entire thing is a strongly connected component. Is there a question?
Is there a way to figure out the DAG of SCCs just from these numbers, or do we have to go through the algorithm for finding SCC?
I don't think you can do that for all the graphs, but for some you definitely can, or at least there are some structures you can discover. For example, like you can see that A has the highest post number, so it has to be. Wait, actually, this is not a reverse graph. Scratch that.
There's no way to figure it out from
Mm-hmm.
so we have to reverse them and then
Yeah, sure. But you can see that, well, J has the highest post number. I forgot that. So J is definitely one of the sources. So like these are the things you can use in, yeah, these are the things you can know from these numbers. Okay. Okay, so this is a conceptual question. Just try to prove it, I guess. Okay, so this is basically what the question is asking. So if A and B are strongly connected components, there's an edge from one of the vertex in A to one of the vertex in B. Then the highest post number in A is always greater than the highest post number in B. Try to prove that.
So this is a fine definition. So what sort of
Okay, I've successfully answered one of the questions of Dijkstra, so let's move on to the proof of this one. Okay, so for this graph, there's only two cases to consider. So for DFS, you have to pick a start vertex. It's either in A or B, right? If the starting vertex is in A, then let's see what it says. So if the starting vertex is in A, we can consider two cases. The first case, it goes through all the vertex in A first, and then goes to everything in B, and then goes back, right? So in that case, the post order, because for exploring B, you have to pop off B and then pop off the node in A from the stack. So there must exist a post number that is higher in A. And if the DFS didn't finish exploring the entire component in A and then start to go on components in B, so after it explores everything in B, it'll get stuck here and basically return to this node and start to explore everything else. So it's actually the same case, yeah. Is that clear? Sorry, it wasn't a very good explanation. Cool. Okay, so for the second case, if your starting vertex is in B, then the first thing it does is it'll explore everything in B because they're all reachable from this. And then after exploring everything in B, that DFS run actually stops here and has to repick a new vertex in A to continue the search because these things cannot go anywhere further. And so we have to pick something unvisited, which it has to be in A. And therefore, everything in A starts from a new pre-number and post number. Therefore, the post number in A is higher than the highest post number in B. Is that clear? Okay. Any questions? Yes? Oh, so you're talking about second case, right? When we start in B. So when we start in B, we started labeling these vertex something like that. And then after we finish labeling everything, we haven't labeled anything in A yet, right? So like everything here is say 1 through n. You label number 1 through n, and then everything here is done, and you don't have to touch it anymore. So starting from A, you pick a new vertex, and the pre-number you start with is n plus 1, right? And then from here, this is going to explore everything in A, and after everything, the post number here will definitely be a number greater than n plus 1, which means that the highest post number is greater than the post number in here. Yes. Yes. Is that a question or stretching? Yeah, question? Sorry. Can we all be quiet a little bit? I hear you. Oh. Okay, so this relates to how you implement the DFS search. So remember in the very first few slides, we see that the DFS search is basically, well, you see one node and you put it on a stack. And then, so like basically first of all you have one node on a stack, and then you take it off and you add all its neighbors on the stack. And then you take those off. Whenever you add this vertex on the stack, so the time you add that vertex on the stack is the pre-number. And if you pop it off the stack, it means that you don't have to visit it again. And that's when you assign the post number. So that's, okay. Okay. So here's one more practice on directed acyclic graph. This one is extremely hard as it claims. This is a question actually from the review session when I took the class. And it was very, I'm very impressed by this question. But I don't think we have enough time for this, I guess. So we're gonna take like a 3-minute break and go on to talk about shortest path first. And then if there's time, we can go over this question later. Okay? Cool. You did not see the solution.
What would I?
Yeah, just.
How do you set it? Do I just put it here?
Yeah, just clip it on. There's a.
Can I?
No. Just let them rest for a bit. It's been a long.
Yeah. Great work. So we'll reconvene in 3 minutes, and we'll start talking about shortest path. That's essentially Dijkstra and Bellman-Ford.
If you have any questions, post on Piazza. Or just ask, I guess. 比如说你有一个图是这样的，然后我想让 DFS output 这样一个系统，它可不可能？ 就是它 traverse 或者是这样的一个。
那只要这两个，它的边是全连通的，
它是 underrated， 所以说就没有方向，所以是不可能的。
啊，对，它不是因为是全部连，如果没有这两个边的话，就可以。
对。
所以这个题目是说啥意思？
就是如果你可不可以，就是给你任何一个 tree 在这个 graph 地球上，它能就是建立一个 DFS tree， 让它变成。
We're gonna start soon, so could you leave your question on Piazza? Thanks. Okay, guys, can I get your attention? We're going to resume on the slides. So if you have any questions, please leave it on Piazza, because we're running out of time. Okay, so I'm going to talk about Dijkstra and Bellman-Ford. I found this meme pretty funny when I first saw it. But yeah, an interesting anecdote is that when Dijkstra came up with this algorithm, it turns out to be very concise because he was actually working in a cafe. So he only has a small piece of paper. So it forces him to come up with like a very concise algorithm. So I guess in this case, he doesn't have a lot of time left before the parents are home. So Dijkstra, you can essentially think about it as a fancier version of BFS. We've seen in examples of both the lecture and textbook that BFS is actually going to fail on weighted edges. So essentially the only difference between BFS and Dijkstra is that instead of just using a queue to store all the nodes that you are going to explore, we're actually going to use a priority queue. And why does that work? It's because that when we're using a priority queue, we're guaranteed that when we pop off a node from the priority queue, you're getting the one that's closest to your current node. So that always guarantees like a shortest path from your starter node to whatever node you're exploring right now. And notice that it only works for positive edges. And on negative edges, it's going to fail. I'll give an example later to sort of illustrate why this is the case. A very important thing to remember is actually the runtime of Dijkstra. You've probably seen this a lot of times in textbook, but I'm just going to explain it intuitively why this is a runtime. So notice that for any DFS, BFS algorithms, our runtime is actually just B plus V, right? Because you're actually inserting and popping out all the nodes twice. So when you insert it, it's all the nodes for once. And then when you pop out each of them from the stack or queue, it's the second time. So it's actually 2B and asymptotically it's B. Whereas for all the edges, you're going to examine them exactly once when you're trying to when you're trying to explore further. But where does this log V comes from? So in a binary heap implementation of priority queue, notice that whenever you insert some node into your heap, if you recall your 61B knowledge, there is this bubbling up and down thing that you need to do. So this thing is actually log of V runtime. It depends on how many nodes you have in your heap. And since we're storing all the vertices in our heap, so that's log V. And it's the same thing for all the edges. Because the thing with Dijkstra is that at each exploration, you need to actually update your current shortest path to all the vertices. So when you change the value of these paths, you're also doing what is called a decrease and increase key, which is also going to be log V time. And notice that this runtime is not absolute, because if you have a different implementation of priority queues, such as array or denary heap with like D branches, it's going to be different. There's more examples covered in the textbook, but for time's sake, I'm going to skip that. Binary heap is probably the most important implementation that you need to know. Okay, so we're going to see why Dijkstra sort of fails on this graph. I like these 170 style memes. So when we start from 0, we're first going to add all the neighboring vertices into our priority queue. And then we're going to notice that the edge with the highest priority is actually the edge from 0 to 1. So we're going to explore that first. And the same reasoning for 2. And eventually we're going to come to this node which has a horrifying 50 cost. And notice that the reason why we cannot figure out a shorter path, if you take a look here, it's actually more ideal to go to this edge. If you go to the 50 first and then the negative 99. That's going to give you like a negative 49, and that's perfect, right? Who doesn't want to do that? But essentially the reason why you couldn't do that is because when you start exploring, you're only looking at sort of your neighboring nodes or your neighboring your neighboring edges with the lowest cost. So this cost with 50 prevents you from discovering this better path. If, for example, if we're guaranteed that this is actually the shortest path here, then we can actually achieve a better runtime. And I know that might sound a bit complicated, but I will run another example on Bellman-Ford and show you guys why it works. So yeah, essentially it's gonna fail. Also, does anyone know what this, so imagine if this edge is actually not in this direction, but the reverse direction. Can anyone sort of identify what sort of cycle this is? Yes, it's negative cycle. So the reason why it's called negative cycle is that realize that if you just go on this cycle on and on and on, you can actually achieve like negative infinity score, which doesn't make any sense in real life. So we're also gonna be aware of that. So essentially the bad edge prevents us from seeing the great edge. Okay, so Bellman-Ford is the thing we came up with to actually tackle these sort of negative edges. And the main idea is that you update every edges, and in total, you're running this iteration v minus 1 times. And notice that this v minus 1 times is actually an upper bound. In other real examples, it might often be the case that you terminate way early than this v minus 1 iteration. So what we can actually do is just add a checking condition at the end of this algorithm saying, if during this iteration there's no value that has been updated, then we know that we've actually achieved our optimal updates for all the paths, and we can terminate it early. So this is not gonna change the runtime asymptotically, because in the worst case scenario, we're still gonna need to run it v minus 1 time, but it does make a little bit of difference. So here's the Bellman-Ford pseudocode. You don't have to worry about too much about this pseudocode. Just put it on your cheat sheet and you should be good. Also notice the runtime of Bellman-Ford is v times e. And when your graph is very dense, that means you essentially have a complete graph with all possible edges. That means that the number of your edges is going to be v squared. So in the worst case where you have a very dense graph, Bellman-Ford is going to give you a v cubed runtime. Yeah, just keep these different graphs, whether it's sparse or dense, in mind, because maybe there might be a true or false question that's going to test you on that. Is that clear? Cool. Yeah, so notice that this Bellman-Ford doesn't work for a graph with negative cycles. And why is that the case? Because if you essentially think about a negative cycle, there's not a set value for that path, right? You can just go on and on and on, and your value or your cost on that path can be arbitrarily small or low. So since the path's cost is not even defined, it's guaranteed to fail. And you're just going to be stuck in the infinite sort of recursion or loops when you're doing Bellman-Ford on a graph with negative edges. And I think that should be very intuitive. Does anyone have a question on why it doesn't work on negative edges? Negative cycles? Cool. So how do we actually detect that there is a negative cycle? Notice that what I've just mentioned, the upper bound of the iteration is actually v minus 1. That means that in any graph that's reasonable with no negative cycle, it's guaranteed that you have to iterate at most v minus 1 times. So if you realize that it's still updating value at the vth iteration, then you're probably running into a negative cycle because it's just going to go on and on and on. And notice that what I'm saying here is not that, it's essentially saying that how you terminate early only when there's no updates in the path. So iteration is different from update. And I'll explain that later. but essentially update is on your shortest path to any one of the vertices, whereas the iteration is if you go through all the vertices. So don't mix that. V minus 1 is the number of iterations, not updates. Okay, so let's look at this midterm question real quickly. So given a graph on 11 vertices and 2 ways to label the vertices of G, such that in one labeling the algorithm makes 20 calls to update, while in the other labeling the algorithm terminates in 10 to the power of 2 calls to update. This question might seem not very intuitive, so I'll just make some explanation. Where does this 10 to the power of 2 comes from? Think about this. You have 11 vertices, right? So if you're calling Bellman-Ford on some 1 vertices in this graph, you're essentially finding the shortest path to all other 10 vertices, right? So in one iteration, you're going to update 10 paths to each of these vertices. This is one iteration. So this 10 to the power of 2 is saying that you're running 10 iterations. And why is 10 special here? Because you have 11 vertices and v minus 1, which is 11 minus 1, is essentially 10. So actually this 10 to the power of 2 is the worst case scenario. So essentially what you're being asked to is to have a good scenario where you only have to call 20 updates and a worst case scenario where you have to run through all v minus 1 iterations to have the correct cost for the paths. So let's take 5 minutes on this question. Yes? Why Bellman-Ford works? Okay, so I think to explain why Bellman-Ford works, if you guys know like why it works, you can work on the problem because we only have a short amount of time. But for those of you that are interested, I'll give you a quick example. So notice the reason why Dijkstra works is because say you have some vertices that's like 2 edges away, right? Could be multiple paths. Before you go on exploring this edge, right? Because you have a priority queue, you've already explored all the edges that's like closest to you. So you're guaranteed that this edge here, let's say this is node A, node B, and node C. You're already guaranteed that the shortest distance between node A and B is correct, right? There can be no shorter path from A to B. And how do we know that we can have a correct shortest path from A to C? It's because that for any path that's going to go to C, it has to go through some other nodes near C. That's the shortest, right? So we can have some arbitrary nodes D here, but it might cost us more to get there. So if we actually can find the neighboring vertices of C, the neighboring vertex of C that gives you a shortest path from A to it, then we're guaranteed that this thing is the shortest path for A to C. And this is because that all the edges are positive, right? So it could not, in the negative case, you might go through some other edge that's actually going to decrease your cost. But this is not the case in positive graphs with positive edges, because when you are trying to find the closest graph to C, if you decide that B is not good enough and you're going to some other vertices, that's only going to increase your cost along the way. So that's sort of the intuitive reason why Dijkstra works. And why does Bellman-Ford works? Notice that in a graph with negative edges, this condition fails, right? So the closest node from B to C, such that B has the shortest path to from A to B, is not guaranteed to be the shortest path. Because say if you have some negative edges here, let's call it E, right? With negative like 100. You could actually go through some extra edges. That's going to give you a lower cost. Whereas this is never possible in a graph with all positive costs. You know that intuitively going through more edges is only going to increase your cost, right? So we need a way to actually compute correctly the shortest path, before we reach C. So that's why you are sort of seeing this updating thing in Bellman-Ford. So maybe in the first iteration, you're at least guaranteed to update one node starting from the origin. And say if this is a node, if from A to E, this is a path with 2 edges, then you need at most 2 iterations to get through there. Since you know that the longest path in the graph is not going to exceed the number of nodes you will have. So if this is the number of nodes, you know that the longest path in this graph can at most have v minus 1 edges. Do you guys see how this is true? Because this is basically the case where you have a lot of vertices that's just connected by one edge each, right? So this is the maximum length for a path in any graph given. So if for one iteration you're at least gonna get one edge correct, then for any path that's possible in this graph, v minus 1 iterations guarantees your longest path or the most complicated path to be correct. And that is why it's that bound. So I think once I run through this example, it will be more clear. I'm seeing some confusing faces. Okay, so let's take a look at the answer. So if you look at, let me specify something. So for this Bellman-Ford execution, we're actually breaking ties by alphabetical order. So that means that we're gonna check A first, and then B, and then C, and then D. Okay, so we start from node A. We're gonna see all the outgoing edges of A, and what sort of shortest path it leads to, right? So we see that A only has one shortest outgoing edge, that's from A to B. So we know that the shortest distance you can get to B from A is this edge, right? And then we're gonna examine C since we're doing alphabetical order. But notice that since A to B is already computed in our first update, and it's guaranteed to be correct because there's only one edge, there could be no possible ways, like A cannot go some other way and then back to B such that it has a shorter path. So now you're guaranteed that A to B is absolutely the shortest. Then you know that from B to C, it's also absolutely the shortest because there's also just one path or one edge from B to C, right? So once it examines C, it's going to examine B, and this is like induction because you know that A to C is absolutely correct, your shortest path, your cost value. So your cost from A to D is guaranteed to be correct, right? And eventually you're going to hit K just by induction. So how many call is this? Just one iteration. Just like an understanding check. Can someone just shout out a number? 10, right? Because 11 nodes in total, and you're doing 10 updates on 10 edges. So where does this 20 come from? Notice that after you finish the call, you need to do another iteration to make sure that there's no further update so that you know you can terminate your algorithm early, right? So you're gonna do another iteration where you're gonna examine another 10 nodes, all the 10 vertices yet again, and you're gonna realize that there's no updates on the value of the shortest path. And that's when you're terminating. So that's how you get 20 calls. Whereas in this example, it's sort of a bit more complicated because remember again, we're doing alphabetical order for exploring. So we're gonna first check A, and we're gonna see that, okay, so A has no outgoing edges. So it's not gonna give us any useful information. And then we're gonna go to B. We see that B do have the outgoing edge from B to A. However, because we don't know what's the shortest path or what's the sort of value from K to B, we'll not know what's the value from B to A. If this seems complicated, recall that before you start running Bellman-Ford, you initialize all the distances to these vertices as infinity. If you recall from the textbook or just the pseudocode. Let me show you real quick. You see how initially you set the distance to all the nodes as infinity? Well, in the first iteration, right, when we are checking B, right, we're gonna calculate the shortest path to A based on shortest path from K to B, and then plus this edge here, right? But since our shortest path right now is from K to B is infinity, infinity plus anything is infinity, so we still don't have any useful information for A, right? So this is also going to happen on the case of C, D, until we examine K. Because K is our starting node, and if you look at the pseudocode here, for your starting node, you're actually having its distance initialized to 0. So what does this mean? This means that you know the shortest path from your starter node to K, which is K to itself, is 0. And then you see that K has an outgoing edge from K to J. so that you know that the shortest path from K to J right now is going to be updated as 0 plus whatever value this edge has, right? But this is the only information we've retrieved in the first iteration of Bellman-Ford. But what about the second iteration? For the second iteration, it's going to happen, the same thing is going to happen because we don't have any information from B all the way to I yet. So when we examine alphabetically from A to H, the distance still going to remain as infinity. However, when we hit I, we're going to see that because we already have the updated value from K to J, so we know that the distance from K to I is just going to be the distance from K to J plus J to I, right? So this induction goes on, so that each time you'll have a new information about one edge, and eventually it's going to take V minus 1 iterations until you get all the correct values for the shortest path. And that's essentially 10 iterations with 10 update calls in each iteration. I know I took some time to walk through this Bellman-Ford, but hopefully this makes more sense now. Any questions? I found Bellman-Ford very confusing because you sort of know the intuition about the algorithm, but not really how you run it on a graph. So if you have time, I'll recommend you to just go on YouTube and search for a Bellman-Ford running example. Once you see how it's actually executed, just like how I show, like you're only using your known information and add on to new information, it will make a lot more sense. Okay, so now let's do another practice. Let's take 4 minutes and I'll explain the solution to this question. Any questions so far? Cool. For this question, think about the infamous the great roads in America example. You could manipulate the graph a bit to achieve what you want. This is a common trick for exam problems. So think about if you couldn't come up with a solution by not touching the graph, how would you actually modify the graph such that you can have an efficient algorithm that computes the distance? Also recall the example on roads in Rome, I think. All roads lead to Rome. That's also in homework, right? It seems to be a similar idea. There might be many grocery stores. It's not necessarily that the entire town or city has only one grocery store. So it could be many. Yeah, but just think about, is that efficient? Because one Dijkstra is V plus E times log V. If you run it multiple times, say you have V houses, that's V plus E times log plus times another V. So I guess think about a solution that you can call as few times of Dijkstra as possible. What time is it? 9:27. Ah, okay. Cool. That's because we're not copying MC, so yeah. We'll resume in 2 minutes. Okay, so may I have your attention? We're gonna resume. Just by a show of hands, how many of you have was actually able to came up with some reasonable algorithm that you deem reasonable? Like, okay, I see a few hands. I'll say this is like more of the hard question level, so don't be disappointed if you haven't. It's not very intuitive, but I guess most people here are not actually interested in the solution itself, but actually how you sort of walk through your thought process to came up with the solution. Because I noticed like a lot of people have been telling me like these homework solutions seems like very arbitrary, and how the heck do you actually think about it, or came up with it? So I'll walk you through like the thought process to approach this question. Okay, so you want to design an efficient algorithm to compute the distance from each household to its nearest grocery store. Notice that in this problem, what makes it very complicated is that we're not just running Dijkstra on one point to retrieve all the shortest path on different nodes, right? We have multiple households, and we want, for each of these households, we want the nearest grocery store. So all of a sudden, it seems like from a problem that you only need one Dijkstra call, it becomes a problem that you need to call Dijkstra so many times that it's not going to be efficient anymore. So we need a way to sort of get around that. So this is, first of all, a shortest path problem, and it's positive edges. So notice that if a question contains negative edges, that is, I won't say probably, that's absolutely the sign that you should use Bellman-Ford, because Dijkstra is guaranteed to fail. So if you want to run Dijkstra once, right, you need to choose a very special starting point. Because if you just start from each household, then you need to run it as many times as there are the number of households. So that's not going to make sense, right? And also notice that it's kind of hard to sort of select the starting point. But there's a clever observation that, in fact, I actually only care about grocery store as my destination, right? I don't really care about, so if I think about the perspective from the grocery store and try to get the shortest distance of each household, that will also sort of work, because the short distance from household to grocery store is the same as like from grocery store to household. And also notice, so I want the grocery store to sort of, if possible, be my starting point. But again, we run into this example that there might not necessarily be only one grocery store, right? So maybe we need a trick to sort of represent the grocery store as a whole, if you see where that's going. So, but firstly, if we're gonna start from grocery stores, the very first thing you need to do is actually to reverse the graph. I think you've probably seen this example in All Roads Lead to Rome homework problem, where you reverse the graph and compute. I think that's a very clever idea, and that homework is like very helpful. So our challenge right now is that there's too many grocery stores, and you only want one starting point. So notice that there is a way to actually merge them. if you add a dummy source vertex to the graph and just add 0 weight edge from the source vertex to each of the grocery store, then this single dummy vertex can actually represent all grocery store. So here's what I mean. You have a bunch of grocery store. They're all scattered across the city, and you want one vertex to represent them. If you have one node such that it's 0 cost to everywhere, that means that if you start from this node, you're essentially starting from any of these points, right? Because from this dummy node to any of these grocery stores, it's 0 cost. So this is how you can represent all the grocery store using just one node. And then you can run Dijkstra starting from S, which is this dummy node, and just find the distance from S to every vertex in the graph. So this reverse graph running Dijkstra is sort of like the thing you've seen in all roads lead to Rome, but except just that for this question, we're actually adding a dummy node to sort of represent all grocery store. So for each household, the distance from S to the household will just be the distance from household to the nearest grocery store. So that's like guaranteed. Is there any question about this? Yes. To the houses. I'll need to think about that. But I think the problem with that is, because if the problem is if you're representing all houses as one node, notice that for a house, for one house, its closest grocery store might not necessarily be the closest grocery store to some other house, right? So if you're representing all house using one vertex, I think there's eventually a problem. Whereas if you reverse it, just like in the case of the homework problem, it's not gonna affect it. Because like, say your house is closest to 7-Eleven, whereas for me, my house is closest to Family Mart, or I don't know, some other Trader Joe's. But like, if you represent both of our houses as one, we're only gonna get one distance to each of the grocery store, right? So that means that you have this one single closest grocery store for all households, which doesn't make sense in the context of a problem. Yeah. Any other questions? Yes. I'm sorry? It's because you wanna run a distance check from grocery stores to house, right? If you don't reverse the graph, notice that this is like if this is a problem of like direct edges, then you only retrieve the distance from house to grocery store, right? Whereas if you're starting from grocery store, it might not be the same path in the original graph. That's why you need to reverse it. All these sort of thinking is pretty similar to the homework problem that I've been mentioning a lot of times. All roads lead to Rome. So if you have any question, check that homework. It should give you a pretty intuitive explanation. Cool. So for any further question, just post it on Piazza and the TAs will handle it. So let's look at another interesting problem from spring 2017 midterm. So suppose that G is a undirected graph with positive integer edge weights. We would like to find the shortest path between two vertices S and T with an additional requirement. If there are multiple, such that if there are multiple shortest paths, we want to find the one that has the minimum number of edges. So notice that the essence of this question is asking you that how do we distinguish one shortest path from another based on how many numbers of edges they contain. It's like coming up with a scheme to sort of break time, which could be really useful in real life. So we would like to define a new weight W prime E for edges so that a single execution of Dijkstra algorithm on the graph G with these new weights starting from S will actually find the shortest path with the least amount of edges. So it's already giving you a hint that you need to sort of modify this graph, especially you need to sort of play around with the weights. So I'll give you 3 minutes to think about how you could actually manipulate the weights such that you can distinguish or sort of tell which path has the shortest or has the least amount of edges.
So for the market thing, I think the explanation is that because we need the information from all the houses, but not necessarily all the grocery stores. So if you run it from the houses to all the grocery stores, it could be the case. It's like going through one of them. Wait, so it was the question from that guy.
Okay, so let's say one or two response.
Yeah.
What I'm saying is like if you represent all the houses once, and you have different distance to each grocery store. There's only going to be one grocery store that has the shortest distance. But if you think about it, it doesn't make sense. Because a grocery store doesn't necessarily have to be shortest to all households. But whereas if you reverse the problem, that thing
No. Actually, it's the exact opposite. So like you can have one grocery store that's closest to everyone. So like this is grocery store. So this is your house. This is your house. This is some other grocery store.
yeah.
So I only care that I can get to this any grocery store. So we cannot run from houses to this because we're not guaranteed to go. So for this supernode, we cannot guarantee that the distance from the supernode to groceries is geared for. And yeah, actually your point makes sense. I see what you mean.
Yeah, but I guess this is very complicated to explain on site, so we should make some clarification of this on site.
Okay.
1 more minute?
Oh no.
We have 20 more minutes, so I think it's pretty good.
Yeah, it's pretty good.
We need to drink some water. Actually, water. Okay, so let us resume. Does any of you have like an idea of where this is sort of going towards? Yeah, so let me just go through it for the people who haven't get it yet. Don't feel bad if you haven't get it. All graphs problems are like very messed up problems, and I think there are definitely like a harder part of this course. But don't quote me on that. So like in midterm 2, don't just come back to me and saying like, oh, there's this other part that's actually harder. So when we think about how we distinguish one shortest path from the other, a very sort of intuitive or sort of straightforward brute force way to think about it is that if we just add some little weight on each edge, right? Then even if you have the same distance towards say 2 shortest path, right? The shortest path with less amount of edges will have this smaller additional weight. So by that, you'll be able to tell which path is shorter. So let us visualize this. Suppose you had these 2 paths on the top and on the bottom. That's of equal distance from the starter node to the termination node. You could just add some small value alpha on each of these edges, such that when you actually compute the distance plus all these additional weights, the number you're gonna get is that this shortest path, this shortest path with less amount of edges is gonna have plus 2 alphas, right? Because you have 2 edges here. Whereas here you're gonna have plus 3 alphas, right? So using that, we can actually sort of distinguish which shortest path have less amount of edges. But could you guys see like sort of one potential problem that this can cause on the original graph or on Dijkstra? Yeah, so notice that if you add some value that's too large, you could actually change the shortest path's cost value, right?
How can you?
So I'll think about an example, but
I was thinking about this. I'm not sure whether the size of this alpha actually impacts.
This size of the alpha matters because I'll give you a very silly example for now, and I'll sort of show you how to bound this alpha such that it never violates. So notice that if each of these vertices has value, if each of these shortest path have a total cost of 3, right? So 1 plus 1 plus 1 and 1.5 plus 1.5. So that's like 3. If you add some arbitrary alpha, that's like stupid, so like 100, it's I think it's guaranteed to break the balance. Yes. So what you want to do is you want to come up with a design of the alpha such that it's never gonna change the orders. So say you have a lot of different paths, right? If you rank sort of the shortest path on the top, you want to come up with the alpha such that once you add this alpha onto it, it's not gonna change sort of the order of how these paths cost, right? And remember how in Dijkstra, assuming that we have integer weights, these things are bound. If you can actually come up with an alpha such that for any path, the additional weights all summed together is not gonna exceed 1, then you're guaranteed that this order is not gonna be changed. So what is a reasonable number that you guys can think of that will result in adding up all these additional weights on the shortest path will not exceed like 1? Yes. 1 over. No, that is a reasonable bound, but there's a better bound. It's actually 1 over v. Why? Because remember how I talk about in a graph, any longest path cannot possibly exceed v minus 1 edges, right? Because the worst case is just that you have a bunch of vertices that sort of lines up, and you have one edge connecting each. So if you just set it as 1 over v, that means that even you have v minus 1 edge, right? It's going to give you a total value of v minus 1 over v, which is still going to be lower than 1. So that's actually a more reasonable bound than 1 over e, but the idea is correct. Well done. So let's look at the solution. So the idea is that we can have this w prime sub e as the original weight plus the additional weight such that it's 1 over v, the number of vertices. And just as the reason I explained before, because for any path, it could not be longer than v minus 1, so that when you sum it up, it's not going to exceed 1. So that guarantees that the order of these paths is not going to change in terms of like how much, how low their costs are. Yeah. Did I see your question? Yeah.
I still don't quite understand why this thing needs to be bounded.
Need to be 1 over v.
Need to be bounded.
Need to be bounded. Let me try to come up with an example that actually screws up. Or Jialin, do you have any example that could possibly violate this condition? So the question is that why necessarily should this additional weight be bounded?
Oh, so like why 1 over v it can be 1?
Or any arbitrary value.
Oh yeah.
You want to show a counterexample?
There's a question on the discussion worksheet this week. So because it really depends on the shortest path, the number of edges in this shortest path. So for example, if I have
we like to define for this a single starting from S finds the short weight. How should we set that weight?
Yeah. X plus 1. That's like the closest you can get. And even if you make sure that the additional weight is not more than 1, that means that no matter how you add up these weights, it's not going to violate the order. Yes. And I think
this is a valid example. So if you add
do you want to? Oh yeah. So Jialin is showing an example right now on why this should be bounded.
Okay.
Yeah. So the shortest path is actually as so it should be like that, right?
You might want to draw it more towards there so people here
Can people see?
I feel like,
I think it's
did you guys see that graph? Cool. Yeah.
Yeah, if you add 1 to each edge, then the shortest path you get would be this direct edge. but actually the shortest path is going through 3 edges.
Yeah, because when you add 1 on each edge, the cost is going to become 6. Whereas on this edge, it's going to become 4 plus 1. That is fine. So that violates the order. Yes?
Why is it 1 over V and not 1 over E?
So basically we're conditioning, the idea is that for any path that we have in this graph, right, we want to avoid the situation such that when we sum up these additional weights, we have it increase more by 1, right? So we want to bound it by a number that represents the maximum possible length of a shortest path in a graph. Does that make sense?
Oh, okay.
And the maximum length of a shortest path in the graph is v minus 1 edges, right?
Okay.
So that means that if you bound it by 1 over v, then these many edges sum up will give you v minus 1 over v, which is not gonna exceed 1.
Yeah, but wouldn't V minus 1 over E also not exceed 1?
Think about the case where so sometimes depends on if you have. Actually, let me think about it.
Because if there's like
Yes. So notice I didn't say that E is a bound that's not gonna work. I'm just saying it's more reasonable to reason with V. The reason why E is gonna work is that if you think about a longest possible path in a graph, it's also bounded by the number of edges you have, right? You cannot possibly have a shortest path that has more edges than the edges you have. That doesn't make sense. Yeah, so I guess E also works. I think that question will be about whether the graph is dense or sparse.
Okay.
Yeah.
Why is it specifically 1 that you can't cross with like the total?
Okay, so let's show an example here. Also, we're assuming integer weights. So in an integer weight, right? Say you have some shortest path called A. A is not a node or edge, it's a path, right? That's the cost of x, which is the shortest or the lowest, right? What is the closest second shortest path you can come up with? The cost. It's x plus 1, right? So this means that if you increase the value of x no more than 1, it's never gonna violate this order. B will never become the shortest path in this entire graph. If we're assuming integer weights. It can be more complicated with fraction weights. That's a very good question. Yes. So for a tree, the number of edges is v minus 1, right? So if you bound it with E, would that work? I guess when it's a tree, it doesn't really matter anymore. But what you can do is you can try to substitute this E with V, right? So what she is proposing is that if we have a tree graph, can we use E to bound? Let's check that out. So you're saying that this is the additional weight that we should come up with, right? And for the worst case scenario, when we have sort of like the worst case where it's just like nodes line up with edge connected to each, how many edges is that in this longest path? Worst case scenario. It's v minus 1, which is also E, right? So that will, if you sum it up, that will give you a total weight of 1. But why is that not a problem? Because in that graph, you only have one shortest path. Yeah, so it's true. Okay, so for time's sake, I'm gonna move on. For any questions, add it on Piazza. Okay, so this is actually a problem on Mario Kart. I used to enjoy it a lot in my freshman year. I play against my friends in residential hall, but it's not relevant. So you wish to use your knowledge of CS170 to get a leg up on playing Super Mario Kart. In level 17, you must drive through Bowser's castle, which you can model as a directed graph. Traveling through each passage in the castle adds a positive or negative number of points to your score, depending upon what type of monster object power-up is on it. So to successfully traverse the level, you must find a path, perhaps with repeated edges, from the castle entrance S to the exit T, such that your score never goes negative at any point of time. So you can think about your score as like hit points to make sure that your character survives. You never want it to be negative. If you want to put it in like a gaming context, assume that every vertex is reachable from S and every vertex is able to reach T. Use your knowledge of CS170 to design an efficient algorithm to find such a path if it exists, or to determine that there is no such path. A hint is to try to modify Bellman-Ford algorithm. We'll take 2 minutes since we have 5 minutes left. Okay, so let's resume. So basically, you want to use a variant of Bellman-Ford. At each update, verify that the value of the path never becomes negative. So what this means that, remember in Bellman-Ford, you're sort of trying to come up with the path with the lowest cost, right? So at each update, you're comparing it to make sure that your new value is sort of smaller than the old value. Whereas here in this variant, you're actually trying to increase your past cost, right? And why is that the case? It's because that if you think of your character as like a game character, you want to increase the score as much as possible. So at each iteration, when you look at the paths, you want to look for the path that gives you like the maximum cost, right? In this case, cost becomes like rewards, but it's the same idea. So what's the best scenario we can have here? Is that if you have a positive cycle, right? The positive cycle is OP because you can just go inside the positive cycle on and on and on, such that you get enough points that you get like positive and you just exit. You should never become negative. But the idea is that at each update, you want to verify that this never becomes negative. And where's that done? That is done by this condition here. Notice that in the original pseudocode of Bellman-Ford, there's no such statement. But you only want to update if you are sure that this path is going to give you a positive value, right? So this is not necessarily the path to the exit, which is T, because you are checking T here. But that you know that along your way to T, when you're at some other node, that path cannot be negative because you should not be negative at any time. So that is the sort of reason why, even in the for loop, when we haven't sort of finished iteration, we're still sort of trying to see that if there's any path that's like positive. And notice that once we finish the v-1 iterations, we're now going to check, right? If our shortest path to t, or like the longest path to t, actually gives us a positive value. So the reason why we're doing this here is that if this value means like your selected path to t. If it's positive, that means you're good. You can actually go and that you are guaranteed to find a path like that. But some of you might argue saying like, what if, say we found a path to exit that does have like a positive cost, but maybe along the way it's gonna be negative, right? How do we make sure that doesn't happen? We've already prevented this, notice, during each of these iterations, because we're only updating the value of the path if it's positive. So this guarantees that at any point along this path, you're guaranteed that you're positive so far. That's sort of the idea behind. Yeah. Positive cycles. Notice that what's going to happen if there's a positive cycle, or say in the Bellman-Ford case, if there's a negative cycle, you're forever stuck in this cycle, right? But notice how we define this as for I equals to v minus 1. So you're going to do at most v minus 1 iterations, right? So it doesn't matter if there's a positive cycle or not. At most, you're going to enjoy yourself in this positive cycle for v minus 1 time. Then this algorithm is going to tell you, okay, it's time to leave. And you got to leave and check if the value is actually positive. Yes? The last 3 lines? Because remember the problem asks you to identify that if, to determine that there is no such path, if that is the case, right? So what does this, so the last 3 lines is saying the value of v is equal to, this is essentially saying, wait, value of v plus value of u. Okay, so that's saying if you realize that your terminal path to t is not larger than 0, that means it's negative. Does that mean there's no such path? Because this only gets executed if this returns it and doesn't get executed, right? So then you're going to enter another round of check, where you're going to go through all the edges, and you want to see that for v, if it's constantly decreasing, this is essentially saying that because this is an edge from u to v, right? So if the value, if your path value from v is less than the value of u plus the intermediate edge e, it's essentially saying that along this path you've selected, which shows you that the terminal value is negative, right? You're constantly decreasing. Well, that means that you're always getting hit. Your score is always decreasing. And if it happens that you are actually able to maintain your value above 0, that means that although your score is keep on decreasing on this way to the exit, you actually never drop your score to negative, then this will still make sense, because it's only at the very last step, maybe, that you don't have the final value that's less than that's larger than 0. But I think the definition of the problem is that as long as when you reach the last node before the exit, you have a positive score, it's not working. Yeah, so let's check it out. So I guess we're running out of time. Okay, so this is our little gift to you. It's been proven that it seems quite effective on your significant other if he or she happens to be a STEM major. So I wish you the best of luck on tomorrow's midterm, and hopefully we'll crash your graph problems. Thank you. Thanks. Oh.
How do you feel?
I was nervous when I have to explain this thing.
Oh.
I don't quite understand, but I sort of figure it out when I just look at it. So.
Oh, cool. That's
yeah.
impressive.
Thanks. Oh shoot. Sorry, I need to finish the screencast real quick.